Hey there, welcome to another quant reasoning video. This is out of chapter 7 again, unit 7b, combining probabilities. And before we get started, we need something that our book doesn't specifically state in here, but I've thrown it in. It's called the multiplication principle. And basically the idea behind this is that in order to determine the total number of outcomes, remember counting is important, whenever your experiment consists of two or more events, i.e. multiple events. When you have multiple events, we multiply. If you've got multiple events and you want to find out the total number of outcomes, you multiply the outcomes together. And so an example of this is an employee has 5 dress shirts, 3 pairs of pants, and 2 pairs of shoes. How many different possible outfits can this employee construct, put together? Well, what does an outfit consist of? A shirt, a pant, and a pair of shoes. And so there are 5 different shirts and 3 different pairs of pants and 2 different pairs of shoes. And if you multiply that all together, you get 30 outfits. Okay, so very, very simple concept, but you have to remember we multiply when we have multiple events. That's what you got to remember. Okay, and that leads us into the AND probabilities. Now we have to think of it in 2 different formats. When you have independent events, that means that each event does not affect the other one, right? So if I flip a coin and I get a head or a tail, the next time I flip it, what I got before has no effect on what I'm going to get this time at all. Okay, that's an independent event. And so if you have independent events, you simply take the probabilities of each individual one and multiply them together. If I flip a coin twice, right, then that experiment consists of 2 parts, one flip and then the second flip, and you just take the probability of each and multiply them together. This is going to help us not have to construct sample spaces quite as often, what we talked about back in 7a. Okay, so as an example here, what's the probability of rolling 3 6s in a row with a single die? So in other words, our experiment is rolling 3 dice in a row, 1, 1, 1. We have 1, 2, 3, 4, 5, 6 on each side. And so the probability of getting 1 6 is 1 out of 6, because there's 6 sides, and only one of them is a 6. To get 3 in a row, I'd need to get a 6 the first time, and a 6 the second time, and a 6 the third time. And so I get 1 over 6 cubed, which is 1 over 216. So the probability of getting 3 6s in a row if you roll 1 die at a time is 1 over 216. Okay, that's the idea. Now there's a slight shift if we start talking about dependent events. A dependent event is when you change the probability depending on the outcome. So for example, when I'm rolling the dice or I'm flipping the coins, those are independent. But if I'm picking cards out of a deck, if I pick a card and keep it, then the next person has 1 less card to pick from, and they can't pick the card that I picked, obviously, because I'm holding on to it. And so those are dependent events. And when you have a dependent event, you have to adjust the second probability, given that A has occurred. In other words, if I pick an ace of clubs, the probability that you get a different card, that changes depending on what I'm asking about, because I'm holding the ace of clubs now. That changes. That's given A. Okay. So what I want you guys to do is I want you to read through this example. We're choosing 3 people out of a group of 12, 6 men and 6 women. What is the probability that all 3 people we select are men? Okay, so we have 6 folks identifying as men, 6 identifying as women, and that's all that we're picking from. And so what is the probability that you pick 3 people that are all men based on this information? Okay, so I want you to pause the video. I've given you a little bit of hint here, but I want you to pause the video and see if you can figure this out on your own using the multiplication principle. Okay, so the probability that we get a man first is 6 out of 12. Now there's 1 less person to choose from, and there's 1 less man to choose from, so the probability of the second juror being male is 5 out of 11. That's where they came up with that. Okay, and then 1 more person for a third person. There's 1 less man to pick from again, and there is 1 less person to pick from again. And so both of these numbers change once again. All right, and so Then if we want to simplify this, so the final answer is 6 times 5 times 4 over 12 times 11 times 10, but we can simplify this by saying 5 divides into 10 twice, and 6 divides into 12 twice, and then 2 goes into 4, and 2 goes into 4, and leaves a 1 there. And so we end up very simply calculating 1 out of 11. All right, so you can also use your calculator to calculate these and then reduce, but I do expect a reduced fraction, okay, as your answer. All right. So that's how you do multiplicative events and events, whether they're independent or dependent. So now we're going to talk about either or events, and this is different, obviously. Remember, when you multiply, your numbers are getting smaller because they're fractions, less than 1, and remember is very restrictive. Or is not restrictive, right? Or is everybody gets in. It's the union of everything. And so if you have two events that are non-overlapping, in other words, you can't get them both at the same time. There's no possibility, is today Monday or Tuesday? There's no possibility it can be both at the same time, right? So that's what we're talking about. Then if you have a non-overlapping event, the probability of A or B is just the probability of A plus the probability of B. That's it. You just add them together. So for example, what's the probability that you roll either a 2 or a 3 on a single die? Okay, well, think about it. There are 6 sides to the die. How many 2s are there? There's only 1. So there's 1 out of 6 chance that I get a 2, and then there's a 1 out of 6 chance that I get a 3. If we add those together, we get 2 out of 6, which is 1/3. So our probability of getting either a 2 or a 3 is 1/3. And we did problems like this before. We didn't think of it quite this way, but that's the idea, okay? So to go to the next problem, we have to think about the possibility that they do overlap. For example, if I'm picking queens, there's a queen of clubs. But if I'm picking clubs, there's also a queen of clubs, right? So there are 4 queens and there are 13 clubs, but there are not 17 cards here, right? Because the queen of clubs is in both sets. And so remember when we were making our Venn diagrams, then we have to subtract away, and there's actually only 16 different possibilities here, queen or club. All right. So with that understanding, I want you guys to pause the video and see if you can figure out this probability. What's the probability when you pick one card? We're only picking one card here. What's the probability that that card is either a 5 or a spade? Pause the video and try it, and we'll go over it together. Okay? So the probability of a 5 or a spade, right, is what? It's the probability of a 5 plus the probability of a spade, but then we have to subtract the probability that you get both at the same time, because that is possible. There is a 5 of spades card. And so if you got the 5 of spades, that's the same, that's in both of these groups. So how many 5s are there? There's a 5 of diamonds, 5 of spades, 5 of clubs, 5 of hearts. There's 4 out of 52 that you might get that. There are 13 spades. But then there's one card that is both a 5 and a spade. And so you have to subtract that away because it got counted here and here both. 4 plus 13 is 17, minus 1 is 16. 16 out of 52, and that reduces to 4 out of 13. Okay? That's the process. So that handles and probabilities, that handles or probabilities. Now we have one more thing to talk about, and that's the idea of the at least once rule for independent events. So the probability that you get at least one event, A, in N trials. Okay, what's the opposite of getting at least one? The opposite of getting at least one is that we didn't get any. We got none. No A's. Remember the idea, the P of not A plus P of A was equal to 1. Remember we talked about that at the end of 7A, right? So the probability of getting at least one is the probability of not getting at least one, and that's none. That's the probability of getting none. Okay, so you do this because getting at least one, if I only did 2 things and I needed at least one, I'd only get 1 or 2. That's no big deal. But if I wanted like 10 things and I wanted to know if I got 10 choices, what's the probability I got at least 1? Well, I don't want to do the probability of 1 plus 2 plus 3 plus 4. That's way too many. I'm going to do the probability that I don't get any of them and subtract it from 1. That's much easier to do. Okay, so for an example here, we want to find the probability that we get at least 1 head if we throw 3 coins. All right, we toss 3 coins. Then what we need to do, the probability of getting at least 1 head in 3 tosses is 1 minus the probability we get no heads. But what's the probability we get no heads? That's the probability that we get no head the first time times no head the second time times no head the third time. Remember, it's a multiple event, 3 tosses. Or another way to write that would be 1 minus the probability of no head to the 3rd power. So your textbook gives you this power idea, all right, which is great, except that only works for independent events. So I don't want you to memorize that formula. I want you guys to just know how to do it like this using multiple events. So come down here to the bottom. What's the probability you don't get a head? Well, that means you got a tail. So that's 1/2. And so that happens 3 times. 1/2 times 1/2 times 1/2 is 1/8. And 1 minus 1/8 is 7/8. And so the probability that you get at least 1 head in 3 tosses is 7 out of 8. And that makes sense because the only way that you wouldn't is if you got 3 tails in a row, and the probability of that is 1 out of 8. And 1 minus 1/8 is 7/8. Okay? So that's the way we look at it. That's the way we work it. You guys do this problem. The probability of winning a prize on a lottery ticket is 1 out of 10. 0.1, they're giving it to you as a decimal, so you can use it as a decimal. Okay. What's the probability that you get at least 1 winning ticket among the 10 tickets you bought? So you've got 10 tickets you purchased. Each ticket has a 1 in 10 chance of winning. So pause the video and try to figure that one out, and we'll go to the next page together in just a minute and find the answer. Okay, so how do we do this? The probability that we get at least 1 winner in 10 tickets is 1 minus the probability of not winning 10 times in a row. And the probability of not winning, as they mentioned here, is 1 minus 0.1, which is 0.9. So if we take 1 minus 0.9 to the 10th power, that's approximately 0.651, or about a 65.1% chance that if you buy 10 lottery tickets and each of them is a 1 in 10 winner, then you'll at least get 1 winner. You might get 6 winners, you might get 10 winners, but the probability you get at least 1 winner is 65.1%. Okay, now hopefully you guys know that the chance of you winning on a scratch-off is not 1 in 10. It's a lot less than that, right? But anyway, so there's a lot of practice that needs to go into this section. There's a lot of different nuances that we could get, but really we're dealing with 3 specifics: the independent and dependent and probabilities, the or probabilities, both the non-overlapping and overlapping, and then the at least 1 probabilities. Okay, so check out the worksheets in 7B, check out the My Math Lab, and let me know if you have any questions. Thanks, guys. See ya.